So let's first start with the orbital diagram. And the orbital diagram is just when you draw the boxes. So let's say, for instance, let's look at carbon. All right, so the electron configuration for carbon, if I start from the beginning, I'm going to say it's 1s2, 2s2, and then 2p4. So carbon is number 6 on the periodic table. It has 6 electrons. Its electron configuration says 1s2, 2s2, and then 2p2. And guys, to double check yourselves, to make sure you have the electron configuration correct, we know that carbon has 6 electrons, so these superscripts should all add up to 6. So if I add these together, they equal 6. All right, so we're with carbon. If I want to draw out the orbital diagram for carbon, it's basically just saying draw out the boxes. So the orbital diagram just means draw the boxes. So if I'm talking about the s orbitals, there's always one box for the s orbital. We see that it has 2 electrons. The electrons have to be in different directions. When I do the same thing for the 2s, I'm saying same thing. I draw a box, there's 2 electrons, they're pointing in different directions. And then when I get to the 2p, we have to remember that the 2p has 3 orbitals. All p orbitals have 3 orbitals, or all p subshells have 3 orbitals. So I have to draw out all 3 boxes. And remember, when I'm filling out the p orbitals or the d orbitals, I have to fill them out singly first, parallel, meaning I'd say 1, 2 like this, instead of up, down for 2. So then in reality, I just want you to label it and it would look like this. All right, if I did the same thing, let's say for instance, let's just do manganese. Manganese, can you guys help me figure out the electron configuration? Just call it out for me for manganese. It has 25 electrons. If I do the electron configuration starting off with 1s2, what's next, guys?
2s2.
2s2.
Then it's
2p2.
Not 2p2, but 2p, we got to complete the entire row.
Oh, 2p3.
2p6.
2p6, the p goes all the way through 6. So 1, 2, 3, 4, 5, 6. So we completed the first row with 1s2, then we completed the second row with 2s2, and we got to go all the way across the second row, and now it's 2p6. And then it's complete actually. And then we get here, we got to say 3s2, 3p6, and keep going. So it's 2p6, 3s2, 3p6. What's next, guys, if I'm going to manganese?
3p6.
3d.
Say it again.
3d.
Well, completed 3p6 here. So then we keep going from left to right.
Oh, 4s2.
4s2, and then
or 3d.
1, 2, 3, 4, 5.
and then 3d, 1,
3,
3, 4.
1, 2, 3, 4, 5.
All right, so 4s2 and then 3d, 5. Let me know if you guys aren't following what I'm doing. Okay. All right, so remember, we're starting from left to right, and we're trying to complete each row. I'll draw this over here as well. Remember, this is n equals 2, this is n equals 3, n equals 4, so we can see it. Maybe I need to, there we go, that's better. Let me see the whole. So just remember, we have to complete each row. The S block goes up to 2, the P block goes up to 6, and the D block goes up to 10. So if we complete a row for S, it's always going to end in 2. If we complete a row for P, it's always going to end in 6. And if we complete the D row, it's going to end in 10. All right, so if I am trying to draw the orbital diagram for manganese, the orbital diagram, I'm just going to start off with 1s. It's saying 1s, I have 2 electrons. So basically, you have to get the electron configuration correct to be able to draw the orbital diagram correctly. Then I go to 2s. It's also saying that it has 2 electrons. When I get to the 2p, what do you guys think I need to do?
You need 3 cubes,
I need 3 boxes. Yep.
3 boxes.
However you want to say it. In this case, it's full, so I can just say 1, 2, 3, 4, 5, 6. Or you can just draw 2 in at a time if it's completely full. All right, then I get to 3s. I can say up, down, because there's 2 of them. When I get to 3p, I have to draw 3 boxes. 1, 2, 3, 4, 5, 6. 4s, there's only 2. And then when I get to 3d, how many orbitals do you guys think I need to draw for D?
1, 2, 3, 4.
How many boxes do you guys think I need to draw for the D orbitals? Yep. I see Eve wrote it in the chat. We have to draw 5, guys. The one that needs 7 is the F block, but when we have the D block, we need 5. So when I get to 3D, it's 1, 2, 3, 4, 5. And then because there's 5 electrons in it, the way I'm going to draw this out, once again, I have to say singly in the same direction. 1, 2, 3, 4, 5, like this. Okay.
Hello, good afternoon. I was having problem in connection, sorry for that.
Oh, that's okay. And if you miss something, I'll post the recording so you can find it later.
Okay, thank you.
All right. So this is the orbital diagram. We're simply just drawing the boxes for each orbital. I think some of you guys like to just memorize the order. The order is going to be the same for the most part. So I'll write down the order for you guys, meaning anytime we're going to go do the electron configuration, if we know the order, it's pretty simple to do. So order is always going to be 1s, then you write 2s, then 2p, then 3s, then 3p, then 4s, 3d, 4p, 5s, 4d, 5p. And if I kept going, you'd say 6s and 4f. But in reality, if I'm looking at it in the periodic table wise, it looks like this. 1s is the first row. The second row is 2s and 2p. The third row is 3s and 3p. The fourth row is 4s and then 3d and then 4p. And if I kept going, I would try to squeeze in 5s, 4d, 5p. So if we're looking at it at the periodic table wise, we're saying this first row is going to be 1s. Then the second row is 2s, and then you go across to 2p. And then the third row is 3s, and then you go across to 3p. And then the fourth row is 4s, and then you got to say 3d, and then back to 4p. That's what I'm saying when I write it like this.
Okay.
Okay, this helps.
Yeah.
Mhm.
And so just remember that S's are always going to be 2. P's are always going to end in 6. That's if you complete the row. And D is going to end in 10. So for instance, if I went back up to manganese, manganese is in the 4th row, and it's number 5 in the D orbitals. So I know that it's going to be all of this up to 3d5. Does that make sense? So it's going to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d5. And I know that because if I go to 3D, I know this starts at 3D. That's 1, 2, 3, 4, 5. That's where my electron configuration is going to end at 3d5. And if I know the order, I can just fill in everything else and end at 3d5. You guys following what I'm saying? I can't tell if you guys are following me.
Yeah, I understand.
Okay. All right. So that's the orbital diagram. Now, another way to write out the electron configuration is to write the abbreviated version, because as you can see, the further you get down the periodic table, like let's imagine I had to do the electron configuration for iodine. That's a lot of letters and numbers I have to write out. So we have an abbreviated version or noble gas configuration. That is a much simpler way to write it. And you're basically writing what it ends in. So if I'm saying the noble gas / abbreviated, it just depends on where you're looking, how they say it. Abbreviated configuration says that if I look at the noble gas of the previous row, I always have to go to the noble gas of previous row and put it in brackets. So remember the noble gases are column 8. That's the last column on the periodic table. These are the noble gases. So it's saying that I go to the noble gas of the previous row, put it in brackets, and then I write everything after that. So for instance, if I'm looking at phosphorus, if I'm looking at the electron configuration for phosphorus, we know that the electron configuration for phosphorus, if I just go in order, I can say 1s2, 2s2, 2p6, 3s2, 3p3 is where it's going to end. So it's saying 1s2, 2s2, 3s2, 3p3. Now, if I write, this is the regular configuration. If I write the noble gas configuration, I'm saying, okay, I don't want to write all this out. I'm going to write the abbreviated version of it. And that means I'm going to look at phosphorus and then go to the previous noble gas in the previous row. So in that case, the previous row's noble gas is going to be neon. I'm going to write neon in brackets. And I'm going to say, if I wrote this correctly, sorry guys, 2s2, what did I say? 2s2, I forgot my 2p6 here. Here we go. Okay, let me write this out better so it's clear. 1s2, 2s2, 2p6, 3s2, 3p3. That's what it should look like instead. Now, if I go to the noble gas of the previous row up from phosphorus, that's going to be neon. And in reality, neon's noble gas configuration or neon's configuration is simply 1s2 all the way to 2p6. And I can look at the table and see it's 1s2, 2s2, and then 2p6. So basically, I'm saying this is just neon. There's no point of writing all that out again. So I can write neon in brackets and then just write the rest of it. 3s2, 3p3. So that's why it's called the abbreviated version, because it's like, there's no point of being redundant and rewriting all this. Just know that this first couple letters is neon, and then add this on, and that'll make it phosphorus. All right, so let's do another example. Let's go back to manganese. I think manganese is a good one. Let's go back to manganese. We said previously that manganese's electron configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then 3d5 if we went to manganese. And then if we look on the periodic table and we go back to the noble gas in the row above manganese, what's the noble gas in the row above manganese?
Argon.
Okay, it's argon.
Argon.
So that means I can write argon in brackets, and essentially all of this is argon. This is all argon right here. So I'm going to say argon and then just write 4s2, 3d5. So basically, if I look on the periodic table to figure this out without having to write out the long extended abbreviation, I would just go to argon and say, okay, argon in brackets, what comes after argon before I get to manganese? I'd have to say, I'm on 4s2 right here, and then 3d, 1, 2, 3, 4, 5. You see it?
Yes. So do we always go to the last gas?
Yep, the noble gas. We go to the noble gas of the previous row. It has to be the previous row.
Okay.
All right, so I can't go to krypton and talk about what manganese is going to be because it hasn't gotten to krypton yet. I got to go to argon and then continue from argon. So we always have to go to the previous row, is all I want to make clear. And also when we're writing out the noble gas configuration, let's say for instance, I want to write out the noble gas configuration for a noble gas like argon. I cannot just say argon. I can't just say, oh, it's just argon. That's the noble gas configuration. I'd have to actually go to the noble gas of the previous row, which in that case would be neon.
Neon. Okay.
It would be neon. And then when I continue from neon, you guys tell me what it would be if I continue from neon to write out to get to argon. What's after neon?
3s2.
3s2.
Uh-huh. So 3s2, that's right. And then what's after that? If I keep going to get to argon.
P 4p.
Not 4p because argon's right here on level 3.
3p. 5.
Not 5. Argon's right here. It's the last one. So it's going
Oh,
to be
6.
3p.
3p6. Okay.
Okay. All right. So this is the noble gas configuration. Remember, the whole point is go to the noble gas of the previous row and put it in brackets. All right, so do you have any questions before I keep going? All right, so this brings us to ions, guys. So remember, we can write electron configurations for ions as well. When we have an ion, it's basically saying, remember, we got a positive or negative charge.
Mhm.
All right, so ions have a positive or negative charge. Remember, negative means extra electrons. Positive means missing electrons. That E minus stands for electrons. So if I have ions, like for instance, a sodium ion, Na plus. Sodium is number 11 on the periodic table. If we look at the periodic table, it's number 11. Normally, we think it has 11 electrons. But if it's an ion of sodium, how many electrons would it have, guys?
10.
It would have 10 electrons. It's missing one. So if it has 10 electrons, that means it has the same number of electrons as neon. So the electron configuration for sodium ion is going to be the same electron configuration as neon. Those same 10 electrons, we'd write out starting from the beginning, starting at 1s2, and then we go you start at 1s2, and then you go to the next row, it's 2s2, and then you keep going, and you go all the way 2p, 1, 2, 3, 4, 5, 6. So the electron configuration for a sodium ion is 1s2, 2s2, 2p6, which is the same electron configuration as neon. Same thing when I do an oxygen ion. You guys tell me how much this oxygen, how many electrons this oxygen ion is gonna have.
10.
All right, so we look at oxygen. Oxygen's number 12 on the periodic table. I'm sorry, number 8 on the periodic table. Normally oxygen has 8 electrons, but because it's 2 minus, it's gonna have 10 electrons as an ion. So those same 10 electrons have the same configuration as neon, as well as the sodium ion, which is 1s2, 2s2, 2p6.
Okay.
The electrons are going to occupy the same orbitals. You're just taking some away or adding some. And since they're going to go in the same order, it's like you add 2, so you're going to add 2 like you would for neon. And if you're taking away 1, you take 1 away. And it's going to go in the same order every time. All right, let's see if you guys can do the electron configuration for calcium 2+ ion. So you guys spend a second and see if you can write out the electron configuration for calcium 2+. So we're trying to figure out the electron configuration for calcium 2+.
I think it will stop at argon.
What's that?
I think it will stop at argon.
Yep, so okay, it has the same electron configuration as argon because it's missing 2 electrons. So 20 minus 2 equals 18. It's gonna have the same configuration as argon. So what's the configuration for argon? Starting with 1s2.
1s2, 2s2, 2p6, 3s2, 3p6.
Perfect.
That's right.
All right, great. So that's 18 electrons. We say 1s2, 2s2, 2p6, 3s2, 3p6.
We always write ionic configurations in the noble gas abbreviated form, or does it?
Well, this isn't the noble gas abbreviated form. You don't always write it any kind of way. You just write it however the question asks. If I wrote the noble gas abbreviated form, it would say, okay, the noble gas above argon is neon, and then I'd write it like this. This is the noble gas. You have to have the noble gas there to make it a noble gas abbreviation. This is the way you just called it out. That's just the regular electron configuration.
Sounds good.
Okay. All right, there's 2 exceptions I want to tell you guys about, and then I want to just do some quick examples on that worksheet that I gave you guys. So the exceptions that I want to tell you, because everything in chemistry has an exception.
Excuse me, Professor?
Yep.
Okay, for that one, for calcium,
Mhm.
should it start as in the brackets and argon or neon, or is it the same thing?
It should start as neon, because remember, calcium 2+ has the same configuration as argon. So if we just put argon there, it would just be argon in brackets. So we got.
Okay, okay, I see.
And in
Okay,
reality, I wouldn't ask you to write a noble gas of an ion. I would just make you write the regular way.
okay, thank you.
All right, so then we have the exceptions. The exceptions say some of the d orbitals, or not even some, just the d orbitals in general. D orbitals prefer to be half filled or completely filled. So remember the d orbitals, there's 5 of them. There's 5 d orbitals. You always got to draw out 5 boxes. 1, 2, 3, 4, 5. If they're D, doesn't no matter if it's 3D, 4D, 5D, 6D. They like to say 1, 2, 3, 4, 5. This is half filled. And if it's completely filled, that means, you know, all 10 are filled in. And it would say like this. So this is what I mean by half filled or completely filled. All right, so in this case, when we have these d orbitals, the exceptions that your class has to know is chromium and versus copper. Chromium. If I were to draw out the electron configuration for chromium, you guys look at the periodic table and tell me what you think the electron configuration would be for chromium. Starting with 1s2. Put this up here for you guys. If we're going to chromium, right here, what do you think the electron configuration is going to be for chromium? Just if we go in order, guys, starting at 1s2, what's next?
2s2,
Then 2s2, then what?
2p6.
2p6.
Then we go back to 3s2,
Yep.
P6.
3p6,
Okay. Say it again, Puan.
S2.
4s2,
4s2.
and then
and then 3,
D5.
4
3d.
3d,
And you guys see 1, 2, 3, 4. Chromium. 3d4. All right, so that's what we think the electron configuration is if we do it the regular way. But in reality, because the d orbitals prefer to be half filled or completely filled, you see this is 3d4. What ends up happening is it's going to take an electron from the s orbitals. So it's going to take one of these electrons so that it can be half filled. So instead of it saying 4s2 3d4, it's going to say 4s2 3d5. So it's all of this, and then, sorry, 4s1 is what I'm trying to write. 4s1 3d5. So it took an electron from the s so that it could be half filled. It wants to do that because the atom is more stable if the d orbitals are half filled or completely. So same thing happens with what's right under chromium. I think same thing happens with this one and with tungsten. So it would be 4s4, I mean it's 4s 4d 4, what is this? 4s 5s 5s1 4d5 6s1 5d5 is what I'm saying. Now when you get to copper, you see copper would normally be D9. You would think it's D9, but in reality, it prefer to say D10 because it's more stable if it's D10. So it's going to take an electron from the s orbital as well, and it's going to say 4s1 3d10, 5s1 4d10. But the only ones you guys have to know are copper and chromium. So if I write it out for copper, here I'll write copper over here. You would normally think copper is the same way, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and you would think it's 3d9. But just like chromium, it wants to be either half filled or completely filled, so you're gonna take one from the s, and it's actually gonna be 4s1, 3d10. So it prefer to be this one. Guys, stick a star next to this. These are gonna come up on the test on Thursday. Put a star next to it because it's just a simple question.
This is applied only for these two elements or other also D block elements?
Well, it's for the ones that are in this column. So silver is right underneath copper. Silver is gonna say 5s1, 4d10. I don't think gold does it. Gold might do it, but for the ones that are in this 4 and this 9 column. But the only one you guys have to know is chromium and copper. And like I said, I'm making it a question on the test. I tell you guys every semester, put a star, put a big star next to it and say, this is a question on the test. You guys forget, and then you go ahead and write it the way like this, and you end up getting it wrong. All right, so do you have any questions before I keep going? A few things, let me just recap right quickly. Remember I said that each orbital has a maximum of 2 electrons and they have to be in opposite directions. This is called the Pauli exclusion principle. And just in case it comes up, max of 2 electrons with opposite spins. In each orbital. Pauli exclusion, there we go. All right, let's see. The last thing I want to talk about in chapter 9 are the periodic trends. Let me quickly go through these and then we'll take a break. Periodic trends. So from the electron configurations, and we figure out how the electrons reside in atoms, we have come up with what is known as periodic trends. And it's just what it sounds like. It's the trends that happen across the periodic table. The first one I want to talk about is the atomic size. Atomic size is what it sounds like. It's the size of the atom. So the size of the atom is basically saying if you go from the nucleus, and it's saying the electron that's furthest away from the nucleus. That determines the size of the atom. All right, the electron that's furthest away from the nucleus, is from the distance from the nucleus to here, that's the size of the atom. When we talk about the trend for atomic size, as you go down the periodic table, remember as we go down the periodic table, the energy levels increase. It goes from 1, 2, 3, 4, 5, 6, 7. The energy levels increase. So the bigger the energy level means the bigger the atom's going to be. Remember, we're saying like n equals 1 is here, but then when you draw n equals 2, it's a little bit bigger. N equals 3 is a little bit bigger than that. So as you go down the periodic table, the size increases. But then when you go across the periodic table, if we go across the periodic table, let's say we're in the same energy level, like n equals 3. If we go across the periodic table, what happens is you get more electrons. You go from 11 to 12 to 13, 14, 15, 16, 17, 18. We get more electrons. And the more electrons you have, that means you have more of a negative charge on your positive nucleus. So this positive nucleus pulls in more of the electrons. We say that the size decreases. So the attraction is stronger to the electrons because you have more electrons. So the more electrons, the more the nucleus pulls on those electrons and it pulls it in tighter. Whereas even when you have more electrons, but you go to different energy levels, the size of the atom gets bigger. So if I did a few quick examples, just saying, oh, which atom's going to be bigger? Circle the larger atom. Let's say if we want to compare carbon or oxygen. If we look at carbon and we look at oxygen on the periodic table and we want to figure out which one's going to be bigger.
Carbon.
Yep, so all we have to do is we look at the periodic table, we see that carbon and oxygen are in the same row. Since they're in the same row, it says that you go across, the atom decreases, so carbon's going to be the larger atom. But let's look at lithium or potassium. Somebody else tell me what they think the larger atom's going to be between lithium and potassium.
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 Yep, it's going to be potassium because if we look at, they're both in group 1. As you go down, the atom gets bigger. So we're going to say potassium is bigger. All right, let's see carbon or aluminum right quickly. Let's see if you guys can figure out carbon or aluminum.
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 Okay, yep, it's going to be aluminum. If we look at carbon versus aluminum, we start off with carbon. As you go down, we know it increases, but then also as you go to the left, it also increases. So aluminum is going to be bigger than carbon. Now, if we went the other diagonal, we wouldn't have enough information. Let's say we're trying to compare carbon versus phosphorus. As you go down, it increases, but then as you go to the right, it decreases. So it's like +1, but then -1. So we couldn't look at the periodic table to see if there was enough. There's not enough information to enter carbon versus phosphorus. So diagonals, it kind of depends on which way you're going on the diagonal. If you're going to the right, you don't have enough information. If you go to the left, you have enough information. You guys see the difference in the two I just gave you?
Yes.
All right. All right, so that's the first periodic trend. The next one is ionization energy. Ionization energy is saying that how much energy does it take to turn an atom into an ion? So basically, let's say, for instance, I want to take sodium and change it into an ion. It's saying how much energy is it going to take to take an electron away from sodium? So to figure that out, it has the opposite trend as atomic size. As you go down the periodic table, the atom gets bigger. So if the atom gets bigger, that means this electron that's furthest away is further away. The further away the electrons are, we can say the less energy it takes to take that electron from the nucleus. The more distance between the electron and the nucleus, the less energy it takes. It's like, oh, I don't have to try that hard. The nucleus isn't pulling so hard on the electron. But then when you go across the periodic table and the atom gets smaller, meaning the electrons are held tighter by the nucleus, it takes a lot of energy to take those electrons from the nucleus. So we say the ionization energy increases as you go across. So these two have the opposite trend. And we can do a few quick examples. Just saying which one has higher circle, the higher ionization energy. Ionization. Let's say we're talking about magnesium or phosphorus. What do you guys think between magnesium and phosphorus?
Phosphorus.
Phosphorus, they're both in the same row. So as you go across, it increases. Let's say arsenic versus antimony. So that's AS versus SB. What do you guys think?
AS.
AS, yep, that works. So you guys get it, periodic trends. You just got to know what the trend is. And if you know the trend, it's easy to figure out what the answer is. All right, and then finally, the last one I want to talk about is metallic character. The last trend is metallic character. Metallic character is simply just saying how metal-like is your atom. And if we just look at the periodic table, remember that when we talk about metals versus non-metals, on the left side, we have metals, but then on the right side, we have non-metals. So as you go from left to right, it goes from a metal to a non-metal. So we're saying that the metallic character increases as you go, decreases as you go from metals to non-metals. But then as you go down the periodic table, these metals become larger with mass and size. So we say it increases as you go down the periodic table. So I'm going to say it increases as you go down, decreases as you go across, same trend as atomic size. So the question says, choose a more metallic element, Ge or In, and then Ga versus Sn. You guys let me know what you think.
IN.
All right, so if we look at the first one, we're looking at germanium versus indium. So that's Ge versus indium here. So as we go down, we can say it increases. As you go to the left, it also increases. So the first one, yeah, we're gonna say it's In. What about the second one? We have now gallium versus tin. What do you guys think for gallium versus tin?
10.
All right, so if you go over, we're gonna go ahead and decrease. Then as you go down, it's gonna increase. So if one increases and the other decreases, you know, that's gonna cancel each other out. So yeah, Eve, it's not enough information for this one. You guys see what I mean?
Yep.
All right. Any questions on periodic trends? That's what they are. They, the periodic trends, we just got to memorize them. You got to know what they are and be able to read it from the periodic table. It's easier if we understand what's actually happening with the periodic trend. You know, atomic size is just saying how big is your atom. Ionization energy is saying how much energy does it take to turn your atom, your neutral atom, into an ion. And then metallic character is just saying how metal-like is your element.